Today, we want to talk about hacking small office, home office, SOHO areas, and especially we want to enter it from the outside. And we have here Daan and Thijs, and both are working with Computech security, and both are also quite often participated in Pwn2Own. And last time they went to the SOHO challenge, and now they want to present how they entered our home office from the outside, from the WAN perspective. And give a big applause to both of them.
Thank you very much. So, as he described, we work for Contestants. Contestants is a security company in the Netherlands. We do all sorts of security services like pen testing, incident response, that sort of stuff. But Daan and I, we are the research team, so we don't work for customers, but instead we do like general security research on targets that we think are important, that are like a benefit for society if more people looked at it. So that's also why we participate in Pwn2Own and do other challenges like that to find impactful vulnerabilities, get them reported and fixed so they can be addressed. So this event we have, last time at MCH we had 3 talks for different kind of subjects, but it was all a bit much. We didn't get much time to enjoy the rest of the event. So this year we decided we're going to submit, again we submitted 3 of them and they got all accepted. So if you want to hear more about EV chargers, that's tomorrow in the evening, and then on Monday at 2 there's another talk about the same Pwn2Own competition. But for that target we did not succeed during the competition, but we think our research into that target, the EOTech Smart Hub, it was still quite interesting. There was a lot of challenge to get the firmware, so that might still be interesting for other people to learn about. So let's go back a bit and describe what even is Pwn2Own, in case you're not familiar. So Pwn2Own is a hacking competition. It's organized by ZDI, the Zero Day Initiative. And what they do is they set out a couple of targets with a prize amount associated with them. And these targets, in this case, can be all sorts of smart home devices, like smart home hubs, IP cameras. They had routers, NAS devices, printers. And then they just say, if you manage to hack this in a certain way, then you get this prize amount. And they just set out this competition, sometimes without even any involvement of the vendors. So the vendors can participate and cooperate if they want, but yeah, it's not required from them. So yeah, sometimes they do send some representative, and then you can disclose it directly to the vendor, so it can be fixed more quickly. That's always better than having to email it and then it gets forgotten about. And one thing that's special about this edition, so the Ireland edition from last year, is they have this category that's called the SOHO Smashup. In the SOHO Smashup, you don't just hack one device, but you need to hack 2 of them. So you start out with a router on the WAN side, so you're the internet connection for the router. And then once you compromise the router, you need to pivot to an internal device. So they have a list of routers and a list of possible internal devices that you can target. And if you succeed in doing that, and if you're the first in the competition, then you get $100,000. If you're the second team, then the prize amount goes down a bit, so you don't get the full reward. So that's the category that we participated in last year. And we also succeeded, so this is an announcement from during the competition. But of course, they cannot give any details, so in this presentation, we'll go over the vulnerabilities that we found and how we exploited them during competition. But we also wanted to spend a bit of time describing our research process. How do we get started on something? How do we decide we're going to target this NAS or this router? How do we pick them? So we start off on these competitions with a bit of recon, some reconnaissance. How do we decide what we want to target? So we look at a couple of different things for each device, like we see the announcement, and then we start to gather data about those targets. Like, is there any prior research? Did somebody else do a write-up about a vulnerability in a target that they found that might be useful for us. Maybe you can reproduce something like that and then imitate it somehow. But that can also be a downside, because if you find the same vulnerability as somebody else did, and they are earlier than you in a random drawing, then you get a lower reward. So on the one hand, it's good if there's prior research, but on the other hand, that might also mean other teams also look at that prior research and look at the same areas that you're looking in. And we'll go a bit more into that in the presentation tomorrow, or really have to think about, well, other people probably have this bug as well, so do we want to find something else here and dig a little bit deeper? And then, of course, there's also like hackability of a device. So some devices are really locked down, you cannot run anything yourself on there, but other devices, you can just turn on SSH, install your own apps, that sort of stuff. And that makes like debugging on the target a bit easier if you already have any sort of access. If you first need to spend months just getting any sort of access to find vulnerabilities, yeah, that can be a waste of time if you don't find anything afterwards. And then one thing that also really helps is if you can get the firmware easily, like if you can already download the firmware, if it's not encrypted or anything, then we can start looking for vulnerabilities before even buying the device, which might be quite useful if the devices are hard to source. So sometimes the devices, like also in this second point, sometimes they are expensive, but it also can be that they are difficult to get in the Netherlands because it's an international competition. Sometimes the devices are only sold in like North America or something, and then you need to pay a lot in shipping, or it might take a while. You cannot even find a source for them. So that's also something we look at. And price, like the price of the device compared to the reward, that's nothing. But if the device is really pricey and you expect to break a couple before you actually get to the firmware, then it might get important to really think about, is this worth spending any time on this? So then, one of the earliest things we looked at was the TrueNAS Mini. It's called the TrueNAS Mini, but I don't really know what's mini about it compared to the other NAS devices, because it has like 7 drive bays, it has a quad-core CPU, it has like 16 gigabytes of ECC. This thing is like $1,100, excluding shipping, I think. So we did not initially buy this, but we did look around, can we get the firmware? And that turned out to be quite easy because it's an open source project. So you can just go to the website and download like a firmware image that you can even like, install on any PC that you want. It's based on FreeBSD, and yeah, you can just get the source and everything from their website. So it was quite easy to download this firmware, install it in a VM, and get everything set up and get it running. So the way TrueNAS works, if you're not familiar with it, it has a management interface that you can use to control services that you need on a NAS. Like you can turn on the SMB server or the FTP server or whatever. And those are just, most of them are like existing Linux services like Samba for the SMB server that you can just manage from this web interface. And if you can log into this web interface, then you basically have control of the device. There's like an endpoint that you can use to run commands on the device. So yeah, if you have an authentication bypass for this, then you can basically do anything with the device. That's the end goal for us was to get arbitrary code execution on the device, but with just access to this panel, that's enough. So as I said, we installed this in the VM, we explored a bit, we do some port scans to get some idea what's already running on the device. And we also run some packet captures to see, is it communicating with anything, broadcasting anything. And one of the requests that it made out to the internet stood out to us. There was this HTTP request to package.freebsd.org. So initially we thought, well, that must be something built into FreeBSD, it's checking for updates or something like that. But then we looked a bit more carefully and we saw that user agent is Python requests. Looks a bit weird to us, like FreeBSD tools are typically not written in Python. So we decided to look a bit deeper, what is actually making this request? Because it's going over an unencrypted HTTP connection, we could just intercept it and do anything with it that we wanted. And eventually, we figured out that it's part of a software project called IO Cage. This is like a separate project, but it is created by the same maintainers as TrueNAS. And it's like their plugin system. So you can find plugins for various services that you can run on your NAS. And those are written or installed using an IO cage. I think it's kind of like a Docker container, but using jails in FreeBSD. I don't really know the full details. That was not really relevant for what you were looking at here. So as I said, it was downloading a tar file over an unencrypted connection. And we're looking at the source code. So why is it doing this? What it's doing with the package? And then we noticed it's doing this. It's trying to check for updates to the installed plugins that it has. So it's downloading a tar file, it's saving it into a temporary directory, and then it's using the tar file open and then extract all as a Python function to extract all of the files from the tar file. If you look at the Python documentation for the extract all function, there's a pretty clear warning there that you never should extract archives from interested sources without prior inspection, because there could be path reversal in there. So if you have // in there, then it's going to just overwrite files outside of the target directory. As you can see, there's no filter or anything on here. This was vulnerable to this. So by replacing the tar file that it was downloading over that connection, we could overwrite arbitrary files on disk while it was making that request. So we found this after just a couple of hours at looking at this target, and then, we had this vulnerability quite quickly. But then we needed to decide, what are we going to overwrite? So we're running as root. We're not yet in the jail, because this is a process that's managing those FreeBSD jails. So we're still running as root on the host. We can overwrite a lot of the files. It doesn't have like a read-only root partition or anything like that. But for the competition, we only get like a limited amount of time. It's like typically 10 minutes to run your both attacks. So we needed something that would work fast. Like we could like install a cron job or something like that, overwrite the script that would run when it boots. But then you need to wait or trigger a reboot, and that just takes a few minutes, and that's not very nice for an attack like this. So we went for the very non-subtle option to just overwrite the SQLite database for the management interface to set the root password to our own root password. We just copied the database from our own installation. Like for a normal attack, you would not do this because you overwrite the existing data. Like you just hacked the device, but you already overwrote the database that you might have wanted to obtain. But for the competition, this is fine. It doesn't need to be like subtle or anything. So the entire steps for our attack was to just spoof the DNS record for the package.freebsd.org domain, intercept the HTTP connection, serve a tar file with the path reversal to overwrite the database, then use our root password to authenticate. And as I said, it has like an endpoint to just run commands on the device. Just over WebSockets, you can get a shell on the device, and done. So I think this was like just an afternoon to get this to work. But this attack does require us to be a man in the middle. So we need to intercept that outgoing connection to the internet. And that's normally not allowed in Pwn2Own, or you get like a lower reward if you do an attack like that. So that made it really clear for us that we need to combine this with a SOHO Smashup, because if we are the router, then of course we can intercept that connection out to the internet or spoof the DNS records. So our next step was to find a suitable router that we could use for our attack. This is the list of possible routers that you could use for the attack. We bought a couple of them, we looked at a couple of them, but in the end, the one where we found the vulnerability was the QNAP QHORA. And I'll hand over to Daan for that part.
Thanks. Yeah, so we bought the QNAP QHORA. It's a router, it routes packets, doesn't do much else. It's a secure router, but it does come with 6 different vulnerabilities that work on the WAN side, apparent to the competition. So it was the most expensive router on the list, I think. It cost us 600-700 euros or so. So initially, we didn't buy the router. Initially, we just download the firmware from the QNAP website. And plotting the entropy, you quickly see that it's either compressed or encrypted. Turned out to be the latter. There is some unencrypted data at the end, but the firmware is encrypted. So we looked around a bit, like, are there people already figured out ways to decrypt this? Well, there wasn't for the QHORA, but there are decryptors available for most of the other QNAP products. This is just a standard firmware format that they tend to use. The firmware is just AES encrypted, but with a very weak key. Like for most QNAP devices, it's QNAP or something. For the QHORA, the password is QHORA, so that was very difficult to guess. Which raised the question, like, why do you encrypt the firmware if the password is so weak? Like, I understand if you encrypt it because you don't want people to decrypt the firmware, but then you would pick a strong password. So decrypting the firmware is easy, and then you get just a SPASF image of the entire root file system. So that already gave us something to work on. But of course, it's better if you have the actual device, so you can do introspection, debugging, etc. So we bought a device, immediately voided the warranty. So there is a handy labeled debug console connector on the board, which is just a UART. Well, sometimes you see that they lock down UART with either with auto boot and password, etc. It turned out for the QNAP, that's not the case. You get a root shell. It's just your admin password that you set up during initial setup. So that gave us everything to work on. So we have the device, we can see running processes, we can debug, etc., etc. And we have the actual firmware. So we're all set. So we already had we were already quite successful with looking at outgoing connections with the TrueNAS. So we decided to do the same on the QNAP. So these are the outgoing connections that a device typically makes. So of course, DHCP, NTP, DNS, etc. We decided to skip those because finding vulnerabilities in those tend to be difficult and might be easier vulnerabilities in custom developed software by QNAP. So there are two other services that by default make outgoing connections. The first is Cloud Agent, which tries to communicate with the QNAP cloud for syncing services, receiving updates, etc. That is all TLS encrypted, but we know from the past that doing TLS certificate validation is quite difficult, and people tend to mess it up. We have some very cool vulnerabilities in the presentation for tomorrow about exactly this, which also involved some drunk night hacking in Tokyo. So this tends to be misimplemented. So we tried a couple of things, like looking if we can already find some certificates on the device itself that we might be able to use for intercepting that TLS requests. Using your own self-signed certificate typically doesn't work, but using a certificate that's already signed by QNAP, for example, sometimes does work if there is some key material on the device itself. We tried all these tricks as well, but we couldn't get this to work. We couldn't intercept that connection. So there is one other daemon that also makes an outgoing connection, and it tries to obtain a text file from the QNAP website over HTTP. So cool, maybe we can do 2 bugs in a row which involve HTTP. We reversed this for some time. It uses curl to get that file, but unfortunately the content of that file is redirected to dev null. It does store the headers in a separate temp file, but the only thing it does is it runs 2 regexes on those headers to see if it gets a 200 OK and if the content length is something that it expects. And basically this is a daemon to determine if the device has internet connectivity or not. Unless we could find some vulnerabilities in the header parsing, which I think is default curl, we left it as not being interesting because, yeah, the attack surface was just too limited. So, okay, no outgoing connection. Then the next step is, of course, see if we can find any listening services. So there are some TCP services listening on all interfaces by default. Some are quite interesting, but the problem is they're all blocked by the default firewall. So those were out as well. There were 2 UDP services listening. One is Sharon, which is a standard IPsec implementation. We also decided not to look at that one. And one other is called QNWMD. I have no idea what it does, but it sounds interesting. Q1 is their name for their cloud-managed router configurations platform. So that was interesting. So we reverse engineered that for a bit as well. It was nice written C++ with the symbols, so it was doable. So this is the protocol. You can just connect to it over WAN. You can send this JSON message, and then you will get the response at the bottom. I have no idea why this service even exists or what it's supposed to be doing, but this is, I think, the only message that you can send, and then you get the CPU load and memory load, etc. That's the only thing it does. It has some quirks, like if the sender should be an int, but if it's a string, then the whole daemon will crash because some assertion will fail. Looked interesting at first, but we couldn't really get anything more out of this than make it crash. So okay, we have looked at all outgoing connections. We have looked at all incoming connections, and we have nothing. So what else can we do? Well, we can find ways to increase our attack surface. This is a tedious process and also pretty error-prone, as it turned out to be. For example, the first thing we tried is we can hand out IPv6 addresses. Maybe the router behaves differently when it has an IPv6 address. Apparently here we overlooked, or maybe our configuration was slightly different than some other people in the competition, because apparently other people could access the web interface, management interface, over IPv6. It wasn't available for us. I don't really know what that state change might be, but yeah. If you enable IPv6, the web interface is suddenly also a target. You could, of course, focus on traffic from WAN to client-side and not the way around, like deep packet inspection, packet routing, etc. That can, of course, also, wherever packets are being parsed, there could be vulnerabilities. That's some attack surface that we hadn't yet explored, which might be interesting. We could, of course, try various state changes, like we can hand out only IPv6 addresses, block certain traffic, drop packets, try to see if we can force alternative code paths or fallback mechanisms that would give us some extra attack surface to work with. And then you just observe the results, rinse and repeat until you have attack surface that looks interesting to you. So, for example, one of the things we noticed was that there is a service listening, MLMD, on a weirdly looking IP address, which we didn't really know what it was or why it was listening. But looking more closely, we saw that this IP address which was associated to a TUN device. We're like, okay, cool, but what if our DSCP server hands out this IP address to the WAN port of the router? Will this also give us access to that daemon? Well, it turns out it does. That works. So we also looked a bit about in that daemon, reverse engineered quite a bit. It turned out that it is an implementation, we think, of this RFC. I've never heard of it. Basically what it does is it just measures traffic throughput. That's what it's supposed to do. So there is a fixed size buffer, and it continuously reads into that buffer, but with the correct size, and that just happens in a while loop. So the data, whatever data that we actually send to this port never gets parsed. It gets overwritten every new call to read. So there wasn't any buffer we could overflow to create memory corruption. There wasn't any parsing of the data that we sent. So yeah, this also turned out to be a nothing burger. So we had some more attack surface, but still nothing to actually work with. So we've looked at all the outgoing traffic, all incoming listening services. We created some new listening service, and we still had nothing. So we decided to investigate more closely. Maybe we have overlooked something. So we yet again looked at all the DNS requests that the device sends out. Does anyone see anything weird in these DNS requests? Might be hard to read because it's small. We overlooked it the first couple of times we looked at this as well. Yeah. It doesn't triple or a quadruple A record for a local host, which is quite weird. Why would it do this? Turns out it has an entry in /etc host for IPv4 for localhost, but it doesn't for IPv6. Oh, that's interesting. So some services will actually do a DNS request for a localhost on IPv6. So, okay, what if we give the device only an IPv6 address and send a different DNS request for localhost pointing to our server? Let's see if we get any incoming connection. Let's see if this works. Well, it works. We got 2 incoming connections even. One HTTP request on port 6666, asking for scanned devices. And on port 5000, we get an gRPC request. Well, gRPC, that's a binary protocol. You have to reverse engineer what kind of fields it expects, etc. That sounds difficult. Let's see if we can take the easy road here. Let's look at the HTTP request. Who's actually requesting this information and how does it get parsed? Well, it turns out it's a daemon called DM agent. It tries to connect to a daemon called RapidD. I have no idea what this is. I think it's a database service or something. It uses curl get data, and curl apparently does a DNS request, in this case for a localhost. It expects a JSON response with a list of connected devices. I have no idea what it then does with that list. But at first glance, it looks very exploitable. So this is, by observing the normal traffic, this is the structure that it's expecting to parse. For every connected client, it has an object with the MAC address, the OS, the name, etc., etc. And then it uses structcopy to copy all those fields into a fixed buffer on the heap. So we thought this is easy. We have multiple buffer overflows on the heap. This looks very, very exploitable. So it copies each element one by one to a heap struct. So it creates multiple heap structs, one for every device. So we can send multiple objects if we want. It's an array of objects. And the MAC address field that's at the start here actually gets used in a call to Popen as an argument somewhere later on in the code. Only after a sleep of 5 minutes, which is not ideal for us because we're on a time clock, so we might have to wait 5 minutes. But okay, we can work with that. But it turned out that the format is limited to what you would expect from a MAC address. So we cannot just send a MAC address with random shell commands because it will be parsed into a fixed format that doesn't really give us arbitrary command execution. So we thought, maybe we can use one of these structcopies to overwrite the MAC address to make it contain some arbitrary shell commands, and then after 5 minutes, that shell command will get run. It turns out that since the MAC address is at the very top of the struct, we couldn't use a structcopy directly because any consecutive structcopies will just write data after the MAC address. So that doesn't really work directly. So, for example, this is an empty heap, and it would allocate the first device structure. This is how it normally would look. But of course, we could overflow any field into the consecutive heap element. But then the second device would get allocated, and it would just copy the MAC address into that field. And since our struct copy has already taken place, we couldn't directly overwrite the MAC address to get easy code execution. So we need something more for this. Typically what we would do in such a situation is So if the heap already has some random data on there that we don't really care about, but we do control, what we could do, of course, is first send the first element, first device, that would contain normal bogus information. If we could then somehow make the system free the block before the device structure, then the next allocation on the heap would take place before the first device. And if we then use the struct copy, we could overflow into the first field, and then after 5 minutes, we could execute an arbitrary command. So this is how you would typically do this in theory. So we tried around this for a bit, but there is a problem because some fields have to be 0 for this to work. There are some fields in between, and those have to be 0 because otherwise you would trigger an error path and it would bail out. And we cannot really write null bytes because this is a struct copy. It's not a mem copy, it's a struct copy, so it breaks on whenever it sees the first null byte. So we thought maybe we can use the fact that we have consecutive struct copies to write the 0 bytes that we need. So how that would work is, so for the first struct copy, we just write an arbitrary amount of A's, which will contain a 0 byte at the end. But for example, if we want the orange byte to also be 0, what we could do, of course, is use a second struct copy and overwrite until we needed a 0 byte again. And then for the third struct copy, we do that for the last byte as well. And so we could write null bytes at location of, well, what we can choose, can control. But there were a couple of problems. We tried heap shaping, like creating that hole that we needed so that the new device would be allocated before the already existing device. We tried it with HTTP header, JSON fields, etc. But it turns out that this was way more work than we anticipated. We couldn't really get this stable. Also, a problem was that we needed more 0 bytes than we had struct copies, because every struct copy can give us 1 0 of a null byte. So we couldn't write the appropriate amount of null bytes. And the last problem, what really tipped us over the edge to not investigate this further, was that QNAP kept pushing patches, which might change the heap layout, and we need new shaping primitives, etc. So this was the weeks prior to the competition. They're allowed to push updates until the day of the competition, and if your exploit doesn't work against the latest version, you're screwed. And vendors tend to do this as well. These are, every week there was a new update from QNAP, and they all mentioned they had multiple security updates. This is also a strong indication that other teams are trying to mess with you because they don't want you to exploit the same device, because that might influence their chances of winning. So some teams actually burn vulnerabilities beforehand so that they get patched so that other teams will fail. That's a typical strategy some teams use. So, okay, we're not going to look at DM agent anymore. Let's look at that second service, that gRPC service, because that also sounds interesting. So gRPC is a remote procedure call implemented by Google, I think. And it's handled by nm gRPC handler, and it actually tries to connect with Cloud Agent to receive some messages. We dumped the original traffic, and we saw that there are multiple different messages are being exchanged. Some didn't really look interesting. It was just an int or short string. But one call expected some JSON, which was pretty big, and it was called a site info. We didn't really know what it was, but this was how a typical site info looked like, at least on our device. So we first tried the lazy approach, like, okay, fuck it, we're gonna just insert shell commands everywhere, just see if this works. Turns out it didn't, which was a shame, but okay. So we had to investigate this a bit further, and it's actually a quite involved process. So what it does, it writes a site.json to disk. Another daemon will pick this up. That will execute a huge Python file. That will check for modification in this JSON with the JSON that it already had stored. And based on those modifications, it will send out various IPC messages. So it's a very involved process. This is how it typically would look. Energy gRPC handler would talk to Cloud Agent. It would, if it receives a JSON file, it would drop it on disk. That would be monitored by a service called DAS, which is also a C++ binary. That, if it noticed that the file was dropped, would execute a compiled Python script. It says .py, but it was actually .pyc, so it was already compiled. That would take out that whole site.json, parse every field, see if we could somehow, see if it could detect any changes with the current configuration, and if so, it would send out various RPC messages. This was just one of the RPC messages it would send. There were multiple daemons it would contact if, for example, the IP address was changed, etc. I think that this whole setup was meant that in the cloud, you can change the configuration of your router, and that would then propagate to this daemon, and then the correct settings on the device would change accordingly. Of course, in our setup, it would no longer talk to Cloud Agent, but it would talk to us. So we have full control over the message that we send. Maybe this picture is a bit, this is more relevant because we're just YOLOing this. We have no idea what we're doing. But we have quite some power here. The amount of attack surface that we have here is very, very large because there are a lot of fields in those site.json. The JSON file that we had on the device had only a fraction of the fields that it could contain. The problem was it was compiled Python code, and you could of course decompile it, but it is quite hard to read. This is just a small part of a 3,000-line Python file. It would parse all kinds of fields based on configuration, etc. It would send out IPC messages. So we just sat back for a while, thought, okay, let's just take any of those IPC calls that this script is allowed to make, and just see if we can make that happen. Can we construct a valid site.json that will, in the end, do an IPC call to some other daemon that might do stuff that are of interest to us? So we just picked one at random. We said, okay, this call at line 1500 or so looks interesting. It does an IPC call to a binary called RMGMTD. I don't know what it does, what it stands for, etc. But it gives some IP6 information. Let's see if we can make that call happen, and if so, if anything interesting is being done by that daemon with that value. So that turned out to be some work to create a valid site.json. We just picked, so as I said, we just picked one at random, and then we used strays just to see where that output ends up. Do we see anything? Is it being used anywhere of interest? Well, we got lucky in this time. It worked on the first try, as in the first call we did was immediately exploitable. This is the whole exploit. The whole site.json it's a bit involved. You need to make sure that the role is correct. It has multiple sites, and there are some prerequisites to the site.json. But if those are all correct, your output belongs in a arbitrary call to bin_sh. So that gives you arbitrary code execution on the one side.
So we had this vulnerability, and it was like, I think a week, maybe 2 weeks before the actual competition. And then we thought, maybe we should test that TrueNAS exploit on the actual device. We hadn't bought it because it was expensive. We already had the firmware. But it's always good to validate it on the actual hardware. So we assumed that it would work, but it's always good to check. And then it was not even available anymore. It was out of stock anywhere we tried. We couldn't get it. We could order like a similar device. But yeah, that doesn't really give you any guarantees, as other people can attest to. If it's a different version number, then things might work like completely differently, even though you might think that it is the same device. So we didn't manage to actually source a device, so we went to the competition having only tested our exploit on a VM. But in the end, it did work. However, we did get a bit unlucky in the random drawing. So how Pwn2Own works is if there's multiple entries in the same category, then they do a random drawing, and the first successful entry in each category gets the full price amount, and then any later attempts get like either 50% or even 25% of the original price amount. So it's a bit annoying if you're not first, because in addition to the reduced price amount, you also get less if you have the same vulnerability as somebody else. So if you collide on the bug, then you get even less than what you the normal price amount. So this was the other attempts in the SOHO Smashup category. I don't know if it's readable, but yeah, there's quite a few that also targeted the QNAP QHORA, even though there were multiple routers that could be the first step for your SOHO Smashup. There's quite a few that had the QNAP QHORA and the TrueNAS in there. So yeah, we were quite nervous that our bugs would be collisions, because they were so trivial to exploit. Like you do a packet capture on either device, and you can see that HTTP request that we could intercept, or you see the query for localhost. Like to us, the bugs were quite obvious, but it turned out that both of them were unique. So even though we weren't first, so we didn't get the full reward, we didn't lose extra because they were duplicates, which was nice. And we have a short demonstration of both of the exploits here to show them working. In this case, we are not actually chaining them together on the same device, but it's not really technically needed for the attack. It's just for the rules of the competition that was needed. So we're starting the server, waiting for the quad A record for localhost, so it connects to us. Now we're waiting for that request that we can respond to. We send the site info with the payload, and now we get a shell on the device. And now secondly, for the TrueNAS, waiting for the outgoing HTTP request, we set up the connection, and again, we have a root shell. Thank you very much. We are going to publish our write-ups on these vulnerabilities if you want to get more details or read it at your own pace later on. We'll be on our website, sector7.contestants.nl, somewhere in the coming weeks. We don't really know yet. And if you have any questions, then please let us know.
Yes, thank you again after seeing your exploit. And I think we have time for questions. So we have a microphone here and somewhere a second one. So just queue up here in the back for the microphone if you have any questions. In the meantime, we have also a Signal Angel. So if you want to ask questions in the internet, you can send it there. But we have the first question here in the front.
Hi, you said that you ignored all common open source software. Yep. Often they have very old versions of these things in the systems. Is it still hard to exploit and easier to look at the proprietary stuff, or why do you ignore it?
So the question is, why did we ignore the open source projects? Well, we assume that they are more established code bases that more people have looked at. So a lower chance of finding vulnerabilities. Of course, that's not necessarily true in any case, but yeah, we expect that the code quality on these devices for the custom services is typically lower than the open source projects, in our experience.
So even if there are known CVEs or with stuff?
Yeah, so, for example, TimeSync D and System D, if we do find a vulnerability in one of those daemons, then we wouldn't want to disclose those vulnerabilities through QNAP, because that's how the competition works. Then we would go directly to the open source maintainers, because that project is, of course, used all over the place. So we rather disclose those directly rather than through QNAP. So that would also be a motivation.
Okay, so we have, I think, in the back also, no. And not from the internet? No. Then we have one in the front here.
Thank you for the talk first. And you mentioned that needing to hijack traffic or modify traffic was a reduction for the second device.
Yep.
Was it now also one for the first, since you needed to give the device the right IP and everything?
No.
So for the SOHO Smashup, you can just be plugged into the WAN port of the device, so you don't need. So you have like man-in-the-middle capabilities by the setup already. So that's why that was the case. Yeah.
Hey, thanks for the talk. I have two questions actually. For the Mini, it was an outgoing request. Was this something that happened all the time in the back, or did this something that you had to wait for as well?
Yeah. So on the TrueNAS, it would make this outgoing connection just after booting, and then once every day. But because the device takes a while to boot, we were quite confident that we could run our first exploit before it actually got to that point in the second exploit. And it would first do a git clone to get a configuration from GitHub, and then it would use that to get the URL that it would download. And we actually did spend some time writing a script that would slow down the git clone connection slow enough that we could make sure that the last part was actually happening after the first device was compromised. So yeah,
that's pretty cool, but
yeah.
Still a risk in the end.
Yeah, it was still a risk, but yeah, we could tell them you need to turn on this device and then that one, and yeah.
It turned out that for the competition it doesn't matter. They just turn on device. They don't care which device you pop first. Doesn't matter.
Okay, cool. And for the second question,
last
if you don't mind.
Quick question, yeah.
For the emulation, you mentioned you just run it in a VM. Is this something that you also do some research on the device, see how you run it in QEMU or something?
Could be.
So in this case it was really easy because it's meant for like normal x86 PCs, so it was really easy to get installed. But for other devices, typically embedded devices, it's way harder to emulate properly.
So do you normally go for emulation as well then, or
depends on the device.
device?
Sometimes we try, but it can be very hard, very time consuming. So typically we time box it. If we can get it to work in a couple of days, then it's fine. And otherwise we just skip it because it can be a huge time sink, especially if you don't have all the peripherals, of course, which you can emulate. Then it could be a time sink.
Cool. Thanks again.
Yeah, and also thank you for me, and again a big applause for hacking into our home office.